A sharp burst of seismic energy beneath western Nevada has raised a series of precise technical questions that extend far beyond a single magnitude reading. How does a moderate earthquake propagate shaking across state lines? Why do some regions amplify motion while others dampen it? And what does a tightly clustered sequence of more than 150 events reveal about the deeper structure of the crust beneath the Silver Springs Lahontan basin? At 0, 1:29 and 12 seconds Coordinated Universal Time on April 14, 2026, a magnitude 5.7 earthquake struck approximately 20 kilometers east-southeast of Silver Springs, Nevada, or about 12.4 miles. The hypocenter was shallow, at roughly 5 kilometers depth, equivalent to about 3.1 miles. Within hours, the sequence evolved into a dense cluster of seismicity, totaling more than 150 recorded events. Among these, a magnitude 3.9 event at 04:45 Coordinated Universal Time, located about 19 kilometers southeast of Silver Springs, or 11.8 miles, stood out as one of the stronger aftershocks, occurring at a depth of about 6 kilometers, or 3.7 miles. At least 20 additional earthquakes exceeded magnitude 3, while the majority fell within the magnitude 1.5 to 2 range, forming a classic distribution of aftershock decay rather than a diffuse or scattered pattern. Initial waveform analysis and moment tensor solutions provide critical constraints on the mechanics of the main shock. The solution indicates approximately 88% double couple energy, a proportion that strongly favors tectonic fault slip rather than volumetric processes such as magma intrusion or fluid pressurization. The nodal planes are steeply dipping, nearly vertical, consistent with strike-slip faulting accompanied by a minor oblique component. This geometry aligns with lateral shearing of the crust, where opposing blocks slide past one another horizontally rather than vertical displacement typical of pure normal or reverse faulting. Such a mechanism immediately places the sequence within the broader tectonic framework of the Western Great Basin, where distributed deformation accommodates the relative motion between the Pacific Plate and the North American Plate. Unlike the sharply defined boundary along the San Andreas system farther west, this region expresses strain across a wide zone of interacting faults. The Silver Springs area sits within a structurally complex transition belt where multiple fault systems intersect, overlap, and in some cases terminate. The spatial clustering of events offers another layer of diagnostic clarity. Rather than dispersing across a wide area, the earthquakes form a compact, linear to elliptical pattern consistent with rupture along a pre-existing fault plane. The alignment of epicenters suggests activation of a concealed or poorly mapped segment, likely buried beneath basin sediments that obscure direct surface expression. This behavior contrasts sharply with volcanic or magma-driven swarms, which typically display more diffuse volumetric distributions and are often accompanied by inflation signals or changes in gas emissions. No such indicators are evident here, reinforcing the interpretation of a purely tectonic origin. Attention therefore turns to the structural setting, particularly the Carson lineament, and its interaction with the Walker Lane fault zone. The Carson lineament is a significant but less widely recognized structural feature extending across western Nevada. It comprises a series of sinistral or left lateral and normal faults that cut through basin and range topography. These faults are described as intrabasin and intermontane, meaning they traverse both the sediment-filled basins and the intervening mountain ranges, creating a discontinuous but persistent zone of weakness in the crust. Near Silver Springs, the Carson lineament approaches and intersects with the Walker Lane, a major tectonic corridor that accommodates a substantial fraction of the relative motion between the Pacific and North American plates. Estimates suggest that the Walker Lane carries a notable percentage of this motion, acting as a diffuse boundary zone that complements the more localized slip along the San Andreas system. The Walker Lane itself is characterized by northwest trending strike-slip faults, often displaying right lateral motion, and has produced numerous moderate to strong earthquakes over historical time. However, geological mapping and subsurface interpretations indicate a structural complication in the Silver Springs area. Northwest trending Walker Lane faults are not clearly expressed at the surface in this immediate vicinity. Instead, the Carson lineament appears to truncate or disrupt these structures, effectively overprinting the regional fault architecture. This intersection creates a mechanically heterogeneous zone where stress can accumulate in complex ways, potentially loading smaller, concealed fault segments that are not easily identified through surface geology alone. The current earthquake sequence fits neatly into this framework. The main shock likely ruptured one such concealed segment within the broader Carson lineament Walker Lane transition zone. The aftershocks represent adjustments along the same fault plane or on adjacent mechanically linked structures. Their distribution, magnitude range, and temporal decay all align with established models of aftershock sequences following a primary tectonic rupture. Shaking intensity reports provide further insight into how the event was experienced across a wider region. Despite the moderate magnitude, the earthquake was felt across large portions of Nevada and into California. This broad perceptibility is not unusual for events in the Basin and Range province. The crust here is relatively thin and fractured, allowing seismic waves to propagate efficiently over long distances. Additionally, sedimentary basins can amplify ground motion, particularly for lower-frequency waves that resonate within thick accumulations of unconsolidated material. In parts of eastern California, the shaking was noticeable but generally weak, illustrating the interplay between distant geological conditions and wave attenuation. Hard, crystalline rock tends to transmit high-frequency energy more directly, while softer sediments can both amplify and prolong motion. The combination of a shallow depth and efficient waveguides within the crust contributed to the wide felt area. From a mechanical standpoint, the dominance of double-couple energy in the moment tensor underscores the absence of significant non-shear components. This is a critical distinction because non-double couple signals often point to processes such as magma movement, hydrothermal activity, or complex rupture involving volumetric changes. Here, the clean shear signature reinforces the interpretation of a straightforward tectonic event, albeit within a structurally intricate environment. The orientation of the nodal planes introduces an inherent ambiguity common to focal mechanism solutions. Two possible fault planes are mathematically consistent with the observed seismic waves, and without additional geological or geodetic data, it is not possible to definitively identify which plane represents the actual rupture surface. Nonetheless, when integrated with regional tectonic trends and the spatial distribution of aftershocks, a coherent picture emerges that favors alignment with known or inferred structures within the Carson lineament system. Historical seismicity in this region provides important context for assessing the significance of the current sequence. Western Nevada has experienced numerous moderate earthquakes over the past century, reflecting the ongoing deformation within the Walker Lane belt. While large surface rupturing events are less frequent than along the primary plate boundary in California, the potential for damaging earthquakes remains well established. Past events have demonstrated the capacity for magnitudes in the upper 6 range within the broader Walker Lane system, though such occurrences are relatively infrequent compared to smaller, more common sequences like the present one. The question of maximum expected magnitude is inherently probabilistic, tied to fault length, slip rate, and accumulated strain. In a distributed fault system like the Carson Lineament Walker Lane transition zone, individual fault segments may be limited in size, constraining the maximum magnitude of single events. However, the interaction of multiple segments or the activation of longer through-going structures could produce stronger earthquakes. Current geological and geophysical evidence suggests that while magnitude 5 to 6 events are relatively common, the upper bound in this region could extend into the high 6 range under favourable conditions. The present sequence does not, at this stage, indicate escalation toward a significantly larger event. The aftershock pattern is consistent with stress redistribution following the main shock, rather than progressive loading of a larger fault segment. The decay in magnitude and frequency aligns with established statistical relationships governing aftershock sequences, including the Omori law, which describes the temporal decrease in seismicity rate following a main event. At the same time, the clustering of more than 150 events within a short time frame highlights the sensitivity of the crust in this region to stress perturbations. Even moderate earthquakes can trigger cascades of smaller events, particularly in areas where faults are already near failure. This sensitivity is a hallmark of tectonically active regions with complex fault networks and variable mechanical properties. Geodetic data, if available, would provide an additional layer of confirmation by measuring surface deformation associated with the earthquake. Such measurements can reveal the extent of slip, the orientation of the fault plane, and the distribution of strain in the surrounding crust. In the absence of that data here, the seismic record alone offers a robust basis for interpretation, supported by decades of research into similar tectonic environments. The interplay between regional tectonics, local fault geometry, and crustal properties ultimately governs the behavior observed in the sequence. The Silver Springs Lahontan basin sits at a crossroads of structural influences, where the legacy of basin and range extension meets the lateral shearing of the Walker Lane. The Carson lineament adds another layer of complexity, acting as both a conduit for strain and a barrier that modifies the propagation of faults across the region. As the sequence continues to be analysed in finer detail, the broader geological framework of Western Nevada becomes essential for understanding both the behaviour already observed and the limits of what this region can produce. The Silver Springs Lahontan basin does not exist in isolation. It is embedded within the Basin and Range Province, one of the most extensively studied examples of continental extension on Earth. Over millions of years, this region has been stretched, fractured, and segmented into alternating mountain ranges and sediment-filled basins. That long-term deformation has created a crust that is comparatively thin, mechanically heterogeneous, and highly responsive to stress changes. Within this setting, the Walker Lane fault zone represents a fundamental structural corridor. Unlike a single, well-defined fault trace, it is a broad belt of distributed deformation extending from eastern California into western Nevada. Geodetic measurements indicate that a meaningful portion of the relative motion between the Pacific Plate and the North American Plate is accommodated here, rather than exclusively along the San Andreas system farther west. This redistribution of strain explains why seismicity is not confined to California's coastal faults, but instead spreads inland across a network of interacting structures. The Carson lineament adds another layer of structural nuance. It is not a single fault, but a composite zone consisting of multiple sinistral strike slip and normal faults that cut across both basins and mountain blocks. These faults are often subtle at the surface, particularly where they pass beneath younger sediments in the Lahontan basin. As a result, parts of the system remain concealed, only becoming apparent when illuminated by earthquake activity, such as the present sequence. The interaction between the Carson lineament and the Walker Lane fault zone near Silver Springs creates a localized environment where stress can accumulate in irregular patterns, leading to episodic releases along hidden fault segments. The geometry inferred from the recent magnitude 5.7 event fits this structural context with notable consistency. The nearly vertical nodal planes derived from the focal mechanism align with the expected orientation of strike-slip faults in this region. The slight oblique component suggests that extension and lateral shear are occurring simultaneously, a common feature in trans-tensional regimes where crust is both pulled apart and sheared sideways. This combination is characteristic of the Walker Lane system as a whole, where pure strike-slip motion is often modified by normal faulting due to regional extension. One of the most instructive aspects of the sequence is the spatial coherence of aftershocks. Rather than appearing randomly distributed, they define a constrained zone that likely outlines the dimensions of the ruptured fault segment. This pattern can be used to estimate the approximate length of the rupture, which in turn provides insight into the energy released during the main shock. For an earthquake of magnitude 5.7, the rupture length typically falls within a range of several kilometers to perhaps over 10 kilometers, or a few miles to more than 6 miles, depending on the exact stress conditions and fault properties. The clustering observed near Silver Springs is consistent with this scale, reinforcing the interpretation of a moderate, localized rupture rather than a large, multi-segment event. The presence of more than 20 aftershocks exceeding magnitude 3 further supports the classification of this sequence as a classic tectonic swarm tied to a main shock. In volcanic environments, swarms often lack a clear dominant event and may persist with fluctuating magnitudes over extended periods. Here, the hierarchy is well defined. A primary rupture followed by progressively smaller adjustments as the surrounding crust equilibrates. The magnitude 3.9 event, recorded several hours after the main shock, stands out as a typical larger aftershock, releasing residual stress along adjacent portions of the fault. Seismic wave propagation from this event offers a clear explanation for why shaking was felt across a wide swath of Nevada and into California. The basin and range crust, characterized by alternating hard rock and sedimentary basins, can act as both a conduit and an amplifier of seismic energy. High-frequency waves travel efficiently through competent rock, while lower-frequency waves can become trapped and amplified within basins filled with unconsolidated sediments. This dual behavior allows earthquakes of moderate size to be felt at distances that might seem disproportionate to their magnitude. Distance attenuation also plays a role. but in this region it is moderated by the relatively low intrinsic damping of seismic waves. Compared to more tectonically stable continental interiors, the fractured and extended crust of the basin and range allows energy to persist over longer distances. This is why residents in parts of eastern California reported perceptible shaking, despite being well beyond the immediate vicinity of the epicenter. Turning to the question of seismic potential, historical records provide a valuable benchmark. Western Nevada and the broader Walker Lane belt have produced several notable earthquakes over the past century and beyond. Events in the magnitude 6 range are well documented, and geological evidence suggests that even larger earthquakes have occurred over longer timescales. Fault scarps, offset land features and trenching studies reveal repeated episodes of movement along various segments of the system. These records indicate that while moderate earthquakes are frequent, the region is capable of generating stronger events when sufficient strain accumulates on larger or interconnected fault segments. Estimating the strongest expected earthquake in the Silver Springs Lahontan area requires careful consideration of fault geometry and connectivity. Individual concealed faults within the Carson lineament may be limited in length, constraining their maximum magnitude to the mid-6 range under typical conditions. However, if multiple segments were to rupture in a coordinated manner, or if a larger Walker Lane structure were involved, the possible magnitude could approach the upper 6 range. Such scenarios are less common but remain within the bounds of geological plausibility given the regional tectonic regime. It is important to distinguish between possibility and immediate likelihood. The current sequence does not exhibit characteristics that would suggest an impending escalation to a significantly larger event. The aftershock distribution is decaying in both frequency and magnitude, consistent with established statistical laws governing post-main shock behavior. Stress has been redistributed locally, reducing the likelihood of immediate re-rupture on the same segment at a higher magnitude. That said, the broader system remains active, and future earthquakes on adjacent faults are an inherent aspect of the regional tectonic environment. Another dimension worth examining is the role of concealed faults in seismic hazard assessment. Because many structures in the Carson lineament are buried beneath basin sediments, they are not easily mapped through surface observation alone. This introduces uncertainty into hazard models, as the full extent and connectivity of these faults may not be fully characterized. Earthquake sequences like the present one provide critical data for refining these models, effectively revealing the active architecture of the crust through indirect observation. Advances in seismic network density and real-time data processing have significantly improved the ability to detect and locate smaller earthquakes. The identification of events in the magnitude 1.5 to 2 range within this sequence demonstrates the sensitivity of modern instrumentation. These smaller events, while not felt by residents, are invaluable for delineating fault structure and understanding the small-scale distribution of stress. When plotted collectively, they form patterns that can indicate fault orientation, segmentation, and even barriers to rupture propagation. If you found this breakdown valuable and want more clear, data-driven coverage of significant seismic events, make sure to like, share, and subscribe. Tap that hype icon so this reaches a wider audience and keeps more people informed with accurate, no-noise updates.